Now we're going to transition into the chemistry of alkynes. First, there are some terms that you need to be familiar with when we're discussing alkynes. If the carbon-carbon triple bond is wedged in between two R groups, we call this an internal alkyne. If it's on the end, so one end of the triple bond has a hydrogen on it and the other end has an R group, we call this a terminal alkyne. As far as intermolecular forces go, these really only exhibit dispersion. Recall that these are linear molecules because of the sp hybridization of the carbons, and so there's no way that they could have a net dipole moment or anything like we saw with the cis alkenes. The melting points and boiling points of alkynes are very similar to the other members of the hydrocarbons. So for example, pentane and 1-pentyne, you can see, don't have boiling points that are drastically different. And like other hydrocarbons, alkynes are not very water soluble. They don't have any polar groups to interact with water as a solvent. The rules for naming alkynes are basically the same as for naming alkenes, except you use a YNE suffix instead of an ENE suffix. You do need to know that the term acetylene refers to this molecule here, which is the most simple alkyne that we can have. We really only know one way to prepare alkynes, and that's going to hold true really for the whole 2 semesters of organic chemistry, and that's from a dihalide. You can do 2 back-to-back E2 eliminations using sodium amide or T-butoxide. You're using 2 equivalents of these to do 2 back-to-back E2 eliminations, and that will yield the corresponding alkyne. You also can do this with a geminal halide. So notice the positioning of the X groups gets the designation geminal instead of vicinal. You don't know how to make the geminal dihalide yet, and you're going to find that this is actually kind of a useless pathway in the end. In terms of chemical reactivity, alkynes have a fairly acidic proton if it's a terminal alkyne. With a pKa of about 25, you can use sodium hydride or sodium amide to deprotonate a terminal alkyne, and this is going to yield a species that's a very strong base and a very good nucleophile. In this chapter, we're going to be studying the nucleophilic pi electrons attacking different electrophiles, just like we did with the alkenes, and these are going to yield addition products.